Hello everyone, this is case study 6 for the machine learning class, and we are going to be discussing about ensemble learning and boosting and bagging algorithms, and we'll be focusing mostly on ensemble learning and boosting for this presentation. So before we begin, let me just introduce to a concept we are all familiar with, which is decision trees. Uh, and once we look at decision trees and the issues that are associated with a complex or a simple decision tree, then we'll look at what a weak learner is and what a strong learner is. And then we'll divert our topic into what ensemble learning is and why is it required. And then we'll go further into bagging and boosting, which are more complicated and more advanced methods of ensemble learning. And finally, we'll look at the benefits and challenges of boosting, and we'll conclude it with a practical application of decision trees and compare it with ensemble learning and boosting algorithms. So a depth in a decision tree is how you define the complexity of the decision tree. And the depth is basically the distance between the root node and the leaf node in a decision tree. And if the depth is too deep, then this can lead to overfitting, where the model will fit specifically to the sample data that we are training on, to a point where leaf nodes might contain just one or two elements. And this doesn't really generalize our patterns in the data. And this wouldn't perform well when we do it on a data that is unseen before. But if you take a smaller tree to counteract this, then we might run into issues where the data is not properly fit in the decision tree and it doesn't really capture all the patterns in our data. And especially if our data has higher dimensionality, then it might not even take all the features into consideration. Now I'll let Mahendra talk about what weak learners and strong learners are.
So yeah, as Uday said, decision tree can be inaccurate in specific cases. So in the context of machine learning, we have the concepts of weak learner and the strong learner. So basically, a weak learner is a model which is barely better model than random guessing, why? Because it doesn't capture all the data patterns in the data set, and it can't be more reliable. Because of this, when you train the model and when we test on the test data, it has a high bias and low variance, and we can't really rely on that one. Whereas when coming to the strong learner, it fits very well, and it captures all the patterns in the data. And because of this, when we there is a possibility that when we test any data set on the strong learner, there can be low bias, definitely. Why? Because it is capturing all the data, but it can be of high variance with the new test vector, as it is completely overfitted to the training data. So these are some of the specific differences between the weak learner and the strong learner. And when it comes to the strong learner, we have some examples like decision tree with the limited depth, simple linear regression model, and then IV-based classifier. And coming to the strong learners, we have some examples like support vector machines, random forest, neural networks. Usually, these strong learners are pretty complex in implementation, whereas these weak learners are pretty simple and a common man can just interpret by just having a look at this. So when it comes to the context of machine learning, we usually combine multiple weak learners to make a strong learner. And we have so many methods to improve the decision tree, out of which one is ensemble. So I would like to call Sanjay to.
Yeah, so what is ensemble learning? So before getting into ensemble learning, let's understand what were the limitation of the conventional supervised machine learning model. So as Uday said already, one of the main issue with that is overfitting. So what overfitting says is like your data will perform very well for their training data. Your model will perform very well for the training data set, but when you actually deploy it on the real data set, it will not perform that well. For example, your if you want to classify any animal on the basis of its feature, is it a cat or a dog? For the training data set, it will perform very well. But when you actually deploy it and when you give some parameters, um, like its height, breadth, and weight, and everything, it will not perform. It will not give us that kind of results for that data set. The second issue is with the conventional models is, for example, you're using naive Bayes as a classifier. So it will have certain limit for its performance. It cannot go, its accuracy cannot go beyond certain limits. Whereas in that case, you change the model and you go with the other option. For example, a decision tree. So you will go with decision tree, but even decision tree will have its own threshold, its own value, its own accuracy, beyond which it will not go. So what is the solution for this? So ensemble learning is one of the solution which is being used in the industry. So in ensemble learning, we combine multiple models and take the cumulative result out of it. So what happened due to is as we are taking multiple models, so it reduces the chances of overfitting, and eventually it increases the accuracy. So it fulfills our requirement of enhancing the performance. Yeah. So next is like why ensemble learning? So as I said, first it tackles the problem of overfitting. Second, it increases the accuracy, and the third one is uh, as we are combining multiple models, it reduces the variance and the biases which would be arising due to the individual models. So in the next slide, I'll be giving you a brief example how ensemble learning works. So yeah, so I have given over here two examples. First is classification and second one is regression. So what happens is for example, some models work very well for certain features, whereas some other models work very well for the other features. Like in the example, you can see over here, for example, we are feeding like three features, first, second, third, to the decision tree, and we are getting some output like a dog. Whereas for the naive Bayes, we are giving some features like fourth and fifth, and we are getting some result as a cat. From the third model, we are getting dog, and from the fourth model, we are getting dog. So as a cumulative of this, the mode or the maximum, the highly frequent result will be our result. So in this case, we have three dogs and one cat. So the final result will be dog. In similar way, for the regression, what we do is we average all of the model's results and find the whatever the outcome is. So for example, here you can see first model is giving output as a 10, second one is 12, and third one is 16. So we averaged it out and the final answer would be 12.66. So what are the different types of ensemble learning? So basically there are two types, bagging and boosting. So Philip will explain in detail how it works and how we use it in the real scenario.
So bagging and boosting are two popular ensemble learning techniques, and as we saw in the last slide, they are used to improve accuracy and robustness of machine learning models. What bagging is? So bagging is a technique that involves training multiple models on different subsets of the training data with replacement. Each model is then trained independently, and the final predictions the partial predictions are aggregated to produce a final prediction. Bagging tends to reduce overfitting and improves the model stability by limiting and reducing the variance of predictions. The next popular technique is boosting, and it is about iteratively improving performance of a weak model by combining multiple weak learners and forming a strong learner. Each model in boosting is trained on a different subset of the training data, and predictions are combined using a weighted average. So what we saw in the last slide, the second model was using boosting. And boosting tends to reduce bias and improve the accuracy of the final model.
So my name is Shashank and I'll be continuing now. So I'll be doing the introduction on boosting. So boosting is a machine learning technique that aims to improve the performance of a weak learner by combining several outcomes to create a stronger model, as Philip said earlier. Boosting is a subsequent model that focuses on correcting the errors of the previous ones. So to give you an example of how the algorithm works, the first thing is that first a weak learner is trained on an original data set. This could be any algorithm that performs better than the random guessing, but usually the models are like decision tree are used. The first weak learner is then used to make predictions on the training set. The next instances of the first learner misclassified are used to given more weight in the next round of training. The second weak learner is trained on the modified data set and the process is repeated. The second learner is focused on the instances that were misclassified by the first learner and tries to correct those mistakes. The process is repeated until a predefined stopping criterion is reached. At this point, all the weak learners are combined to form a final strong learner that performs better than any of the weak learners. So there are many types and boosting algorithms, so such as ADA boost, gradient boosting, XGBoost, light GBM, and CAD boost. Each type of algorithm has its own strengths and weaknesses, and the choice of algorithm will depend on the specific problem being solved. So ADA boost is the most popular boosting algorithm. It works by assigning weights to each instance in the training set, with misclassified instances given more weight. And whereas gradient boost is also one of the popular algorithm, but uses a decision tree for fitting the residuals for the previous three. And XGBoost is implemented using gradient boosting algorithm, which combines a gradient descent algorithm and a regularization technique to prevent overfitting. And Light GBM is also a gradient boosting implementation, which is an optimized version of it. It uses histogram-based approach. And CAD boost is used to design and handle categorical variables. It is an ordered boosting algorithm to train the models which can handle both numerical and categorical variables. And Yamini will be taking on over the benefits and challenges of boosting.
Coming to benefits and challenges of boosting, ease of implementation. Boosting has easy to understand and easy to interpret algorithms that learn from their mistakes. These algorithms don't require any data pre-processing and they have built-in routines to handle missing data. This approach also helps to reduce high bias that is common in machine learning models. Coming to computational efficiency, they can help in reducing we can reduce data attributes and handle large data sets efficiently. The following are the challenges in boosting. Coming to vulnerability to outlier data. Boosting models are vulnerable to outliers or data values that are different from the rest of the data set. Real-time implementation, boosting methods have high adaptability, so you can use a wide variety of model parameters that immediately affect the model performance. Uday will continue from here.
I just want to show you the results on how we verified this. So we took a basic Titanic data set, pre-processed it, and so this is a basic decision tree with a depth of 10. And then for ensemble learning, we took 100 decision trees by changing the random state. So, and all these results are aggregated and we just take the average. As you can see, the accuracy score has improved a little bit. And as Shashank and Yamini explained earlier about boosting, we can see that the gradient boosting worked even better with a 0.82 accuracy. Thank you all for tuning in. This is the team that did it. Goodbye.
Thank you.